بسم الله الرحمن الرحيم، الحمد لله رب العالمين وصلى الله وسلم على نبينا محمد وعلى اله وصحبه وسلم. معلش نعتذر عن البدايه due to technical difficulties. فنرحب بالدكتور محمد خياط. فالدكتور طبعا معروف للجميع من المتخصصين على مستوى العالم حقيقه في مجال الممبرين ديستليشن ومجال كذلك الممبرين manufacturing and preparation and testing and all that kind of stuff which I don't know at all. Anyhow, Dr. Muhammad, he was the winner of the Prince Sultan Prize for non-conventional water treatment desalination last time. And he was joined us also with a very wonderful and beautiful lecture last year with a lot of people like more than what we have actually here. And we got a lot of interest for your knowledge from the physics department engaged section. I don't know why. But anyhow,
I promise this to you after. When I finish the presentation, I will explain.
Okay, sure. And then I promised them to have record this lecture and put it in the YouTube. And next time we will have some interactive between our department and or the society and the guest section, inshallah, regarding to the membrane. Anyhow, the lecture will be titled Recent Progress in Electrospinning Nanofibrous Membrane for Desalination. I have a translation actually, but I don't know the specialist will agree with me on that or not. In Arabic, I call it التطورات الحديثة للأغشية النانوية الليفية المنسوجة كهربائيا لتحلية المياه. Thank you very much. This is an Arabic translation of the title, and let's welcome Dr. Muhammad for his presentation.
Okay, thank you so much. Assalamu alaikum. So first of all, just I would like to apologize for yesterday because it happened something which it was not under my control, and now everything is okay. So I hope that you will still learn something new about what we have done in the field of membrane installation. So the title today is Recent Progresses of Electrospan Nanofibrous Membranes for Desalination. I think. So I don't know if all of you know something about the membrane distillation, but just only I will give an overview about membrane distillation, and after that I will tell you what we have done in the field of nanofibrous membranes. In membrane distillation, normally we use porous and hydrophobic membranes. Water cannot penetrate inside the pore. Only vapor is transported to the pore. This is single pore, so we have here liquid vapor interfaces, liquid solution, the permeate solution. So this can be salt solution at higher temperature. So the temperature differences generated the driving force, which is the vapor pressure. We have different configurations. Direct contact membrane distillation using water, air gap membrane distillation, water and air. Vacuum membrane distillation, we use vacuum pump in order to permeate, and sweeping gas membrane distillation instead of water running through the permeate side of the membrane. Normally we use sweeping gas. There are a lot of advantages. I will mention here that the most important advantage of membrane distillation is separation factor that must be higher than 99.9. That is normally higher than 99.9%. This means that you can produce distilled water or ultra pure water using membrane distillation. I want to focus more on the disadvantages. The problem we have is membrane flow heating. The liquid temperature for water must be as high as possible for the membrane, or because the membrane is hydrophobic. So liquid temperature of water is inversely proportional to the pore size of the membrane. Actually, it's maximum pore size, And when the membrane is more hydrophobic, then the liquid interfacial water is high. So it's important parameter here that liquid interfacial water must be high. Internal heat loss through the membrane must be as low as possible because we work here with temperature difference. So in this case, the transport of heat by conduction through the membrane must be very low. We have also the problem of vapor pressure polarization. It includes temperature and concentration polarization effect. And long-term operation, we don't know yet what happened with commercial systems which are now available in the market. What happened at long-term for this for this process. The major problem here is no availability of membrane for membrane installation. Therefore, there is an urge to design membranes for membrane installation. When you go in the market, you can find only membranes designed for other processes rather than membrane installation. There is no company selling membranes for membrane installation. And the membrane must be porous and hydrophobic, as I said before. The range of the pore range is between, let's say, 10 nanometers up to 1 micron. As soon as you increase the pore size, so in this case, maximum pore size is also increased, and the liquid interfacial of water, which is the major problem also in membrane installation, goes down. Interest in membrane installation is growing very fast, so we can see here the number of published papers up to December of last year. So we have up to now 750. And the most used configuration, direct contact membrane installation, we have more than 50% of the systems use this configuration because it's easier. You have water at higher temperature on one side and water at lower temperature on the other side of the membrane. This is why we call it direct contact membrane installation. Regarding the fabrication of membrane, you can see since 2003, there is a sharp increase of the number of papers published. We are up to now 127, and about 16.89% of the paper that were published deals with the fabrication of membranes for membrane installation. So there is quite important interest nowadays on the fabrication of membranes for this process. What are the characteristics that membrane should exhibit to be applied in membrane installation? Must be porous, entirely or partly hydrophobic. Single layer or multi-layer membranes can be used. Should exhibit good thermal stability, excellent chemical resistance to feed solution, high liquid interfacial water, as I said before, high permeability. But the most important thing here is the thermal conductivity, which must be small in order to decrease the heat loss by conduction during the membrane. There are different ways in order to decrease this thermal conductivity of the membrane. One can think why we cannot use just membrane material with low thermal conductivity. But most of the materials, they have quite similar thermal conductivity, most polymeric membranes. So the other technique is not so important. You will not get decrease so much, let's say, the heat flux in the membrane just by changing the material. The other possibility is to use thicker membrane, but when you use thick membrane, the permeability of the membrane will go down, because they are eventually proportional. So this is not also interesting. One of the best ways is to increase the porosity of the membrane. The void volume fraction in the membrane should be high. This is why we taught to use nanostructured membrane. And this is, let's say, the core of the present talk. So we started using nanostructured membrane since now 5 years ago. And because these membranes, they exhibit very high void volume fraction, you can go up to 95% of the void volume fraction. And we fabricate these membranes using electrospinning. Mainly electrospinning basically is formed by 3 parts. One is the polymer solution that you prepare, and you fill it in your syringe. Then you have this syringe is connected to circulation pump, you should establish very good flow and precise flow through this channel, because you have here a needle, which acts as electrode, and here the collector, and a high voltage source. We use voltages up to 30 kilovolts. Normally, when you don't apply any voltage, what happens because of the self-expansion forces, you will have spherical structure of the drop. This is, for example, this is the needle, and you have spherical structure you can see here. But when you start applying the electrical voltage, then you have Coulombic forces, you establish your electrical field, and when this Coulombic forces is higher than self-expansion forces, this spherical shape turns to be conical, have conical structure. And when the voltage is higher than certain critical value, you have here Taylor cone, and from this Taylor cone, electrified jets just erupted from this Taylor cone and start to loop. And every time it is looping through this air gap, its size is decreased, and also there is here evaporation, somewhat evaporation, so that this electrified jet starts to solidify. So we collect the membrane either on this collector flat sheet or over drum moving. There are different types of collectors. We have here a lot of forces, not only self-expansion forces and Coulombic forces. We have also electrical forces between charges. And these electrical forces, they are repulsive. When you have the jet, then the electrical jets have charges, and these charges act as repulsive in this case. You have here also the air drag forces, the gravity. So what we have done, we use different types of polymers. We studied the effect of the concentration of the polymer, the solvents, additives. But the most important thing here is that three parameters should be recorded: viscosity, surface tension, and